In this talk, I'm going to present Coarsening, a new way to do differentiable programming developed by Facebook, and explain how this method speeds up differentiable programming by more than 100 times. First, what is differentiable programming? It is essentially a generalized way to inject intelligence into modern software. We know that when training a deep neural network, there is a forward path from input to output. It is also called the primal path. There is also a backward path which computes the gradients of the DNN parameters so that the parameters can be adjusted through gradient descent. Note that the DNN is essentially just a parametric function, and there is no reason why such a training process can be applied only to DNN. If we replace the DNN with another parametric function like this one, which computes the energy of a hooking spring system, using the same gradient descent, we can make the code automatically evolve, such that the locations of the spring vertices can be automatically adjusted, and hence get such a simulation result. There is, however, one key difference. For DNN, programmers don't need to write code to compute the gradients because the code is provided in DNN libraries already. But that's not the case when we allow arbitrary functions to be used as the parametric function. How to get the gradients in such a general case? Ask the programmers to write code to calculate gradients. It's not so easy to do for such a program with while loops and break statements inside. It would be even worse if the primal code is 10 pages long as this code has. Manually writing code to compute gradients becomes impractical. This is the key barrier to realizing the future intelligent software, also called Software 2.0. Differentiable programming comes to rescue. Its goal is to enable automatic differentiation. With a differentiable programming language, programmers need to write only the primal code. The gradients will be computed automatically through simple AD calls. The approach taken by current differentiable programming tools is algorithmic differentiation. Each operation in the primal code is overloaded. For instance, this x plus y becomes such a sequence of operations during runtime. It creates a new object T1. It sets the value of T1 to the primal result, and then it puts a pullback function plus backward into T1. These pullback functions will be recursively invoked later, with each differentiating one single operation. The results are connected together through this chain rule in calculus to generate the final gradients. It is easy to see that this approach incurs many allocations of intermediate objects and also time overhead. There is another approach to differentiation, symbolic differentiation. For this codelet, for instance, this approach applies calculus on the entire math expression to directly compute the gradients symbolically. In this example, the result is y plus 1. We can then write the backward function as simple as a single return statement. No operator overloading or the extra memory allocations or time overhead. Moreover, unlike the algorithmic differentiation case, to get the gradients, there is no need to run the primal code anymore, because the gradients are calculated directly. So if what the program cares about is only the gradients, the primal execution part of the program can be completely removed. But symbolic differentiation requires the computation to be expressed in a closed form, which is difficult to do when there are complicated control flows in the program. As a result, the slower method, algorithmic differentiation, still remains the popular choice. Coarsening introduces a new way to do AD by getting the best of both worlds. The basic idea of coarsening is as follows. For code written in existing differentiable programming languages, it selects some segments of interest or SOIs, raises them to the symbolic level, applies symbolic differentiation and optimization, and then lowers it to source code and replaces the original pullback functions accordingly. It essentially combines algorithmic differentiation with the symbolic differentiation. Even though the idea looks simple, to make it work isn't easy. There are 3 challenges. I'll next explain them each and how our 2 innovations address them all. The first challenge is control flows. For a simple program like this one, it is already difficult to get a closed form of the calculation of variable error because of the loops, if-else, and break. To our best knowledge, no solutions exist that can create a closed form for this example. Now, we invented phi calculus to solve this problem. Phi calculus consists of a set of notations and formulae. It offers the first solution that removes the barrier of control flows for symbolic differentiation. It is built on static single assignment (SSA). Here is a quick review of SSA. SSA is a way to represent code inside compilers. It renames variables such that every static assignment is made to a new name, as illustrated by these names of Z. When there are name ambiguities, such as the Z here on line 10, a special function phi function is inserted. Phi function is only a notation. In this example, for instance, what it says is that the Z5 gets the value of either Z3 or Z4, depending on the runtime execution path. An observation is that if a program is first represented in SSA, then simple substitutions can already produce a closed form. In this example, for Z5, if we substitute it with the phi sub1 function, and then substitute Z3 and Z4 by their corresponding expression and so on. But if we continue doing that, then we can get such a single line expression for computation of L. What about loops? For this loop, here is its SSA form. These 2 phi functions are as the entry of the loop. They are called loop entry phi functions. This phi function is as the exit of the loop. It is called the loop exit phi function. To get the symbolic representation, we introduce a new notation, fetL. So this line says that this assignment is enclosed in the loop. With that, we get this symbolic representation for the computation of S. Now, with phi notations, we get these symbolic representations for these 2 examples, but they still contain phi functions and loop notations. How to handle these notations in symbolic differentiation and optimization? The formulae in our phi calculus give the answer. Here are the 5 fundamental formulae in phi calculus. F2, for instance, says that if an arbitrary function applies to a phi function, we can distribute the function to each of the arguments of the phi function. Formulae F4 and F5 are 2 formulae about loop phi functions. F4 says that for a loop entry phi function in the first iteration of the loop, the phi function must return the value that flows into the loop, represented by A, and in other iterations, it must return the value from the back edge of the loop. We have formal proofs of all these formulae. From these fundamental formulae, we can derive these non-useful corollaries. For instance, C2 is from the distributed formula. It says that the differentiation of a phi function can be computed by differentiating each of the arguments of the phi function. C5 to C9 are derived from the loop formulae. They are useful for removing the loop notations from a symbolic expression. C6, for instance, says that if there is an expression in this form inside the loop, if the loop has n iterations, then the value of D at the exit point of the loop will be in such a form. so the loop notation is removed. Now let's see how the formulae can be used. We have seen that we can get this symbolic representation from this code. With corollary C2, we can easily compute the derivative of L over x by applying differentiation on each of the arguments of the phi function. Then, with the distributive formula, we can distribute the last term into the phi function and hence cancel this denominator, and getting this simplified expression for the computation of the derivative of L over x. And then source code can be easily generated from this expression. The remaining phi functions can be instantiated with if-else statements. For this loop example, with corollary C6, we can remove the loop notation, get this simple expression for the value of S3 as the exit of the loop, and then use the formula F5, we can get the value of S4. Differentiation over x will give the final derivative k. This example is more complicated. It has 3 loops, 1 if-else and 1 break statement. Phi calculus works well still, producing the simplified symbolic expression on which symbolic differentiation can be easily applied. This is the first known approach to deriving a closed form for code with such control complexities. Another innovation, ReuseAware SOI Identification, addresses 2 other challenges for symbolic differentiation. Please see our paper for details. When these techniques are put together, we get an AD optimizer. It takes the primal code as input, identifies SOIs through the ReuseAware algorithm, raises them to the symbolic level, and conducts symbolic differentiation based on the phi calculus, and generates the optimized code with hybrid differentiation. We evaluate the techniques on 6 benchmarks in the domains of deep reinforcement learning, gaming, physical simulation, meta-learning, math physics, and statistical sampling for probabilistic programming. The speedups are significant. Here is the performance on the server. For each benchmark, there are 3 different inputs used in the experiments. The first benchmark is the meta-learner. It has complicated control flows. Coarsening speeds up the differentiation by more than 26 times. If phi calculus is not used, coarsening can be applied to only a small part of the program, and the speedups would drop to about 8 times. On the second and the fifth benchmarks, because what they actually need are just the gradients, and coarsening gives a function to compute the gradients directly, the primal parts in both programs can be removed. On card poll, the optimization can apply to only the non-DNN part of the program. The speedups on that part are 2.6 to 3 times. HMC and QWOP have either large values or long function bodies. Coarsening can apply to them with no problems. Similar speedups are observed on another machine, which is a MacBook Pro, which demonstrates the consistent effectiveness of coarsening across machines. Coarsening can be applied to other differentiable programming frameworks as well. When we applied the coarsening results to BGD HyperOpt benchmark written in these 3 DP tools, we saw 66 to 355 times speedups, even more pronounced than on Difficate. There are 3 final takeaways. First, phi calculus offers the first solution to control flows for symbolic differentiation. It may also benefit uses of symbolic manipulations beyond differentiation. Second, ReuseAware SOI Identification balances coarsening with reuse and mitigates expression swell for symbolic differentiation. Finally, coarsening has proved as an effective optimization for differentiable programming, and hence Software 2.0. It offers a systematic way to combine symbolic differentiation and algorithmic differentiation. It is usable for many existing AD tools. Thanks for your attention and happy to answer any questions.